Welcome to the experiments with acids, bases, and buffers. And acidity is basically a measure of concentration of hydrogen ions. So you know that when you have a high concentration of hydrogen ions, then you have an acidic solution. And basicity will be then the concentration of hydroxide anions. And then for buffers, there will be substances that resist change in pH. So usually when you put a substance that has acid and it lowers the pH, that means the concentration of hydrogen ions is high. Then with the buffers, it doesn't move from a certain amount of, oh my god, I'm losing my thoughts. But anyway, so with buffers, just know that it resists changes in pH. So if you add an acid to a buffer solution, then you don't expect a drastic decrease in the pH readings. And the same thing, if you add a basic solution to a buffer, it doesn't usually raise the pH by a drastic amount. So today we are going to measure the effects of pH change in pure water and also in a buffer solution. So we will use Alka-Seltzer as our buffer to establish our buffer system. And its main ingredient is sodium bicarbonate. So you know that it has an acid or base, and it's conjugate acid or base. And that's basically what causes it to resist the change in pH. So the first thing that I'm going to do is just to obtain pure deionized water and then measure its pH. And there are several ways in which you can obtain the pH of a substance. We have pH meters that gives the accurate readings. Then you also have pH indicators like phenolphthalein that we will use in this experiment. We have a point where we will do titration, and in titration you're basically adding a base to an acidic solution, and you expect that they will neutralize, and when the pH indicator changes color, then you know that the titration point has been hit. So let's begin by looking at the effects of the pH on a buffer and on deionized water. So I will take my 50 mils of deionized water and just obtain the pH reading for this using a pH meter. So here we go. Okay, so just to establish a stable pH reading, I'm not just going to take one pH measurement, but I will also get a pH reading for another 50 milliliters of water and see how different the two pHs will be. If I obtain a pH reading that's 0.5 units difference or less, then I know that my pH is stable. So this one is 7.41. So I'll take another one just to make sure that I'm within the 7.4 pH reading for water. Okay, so this one says it's 7.28, so I know that it's within that range, and I'm just going to record this pH reading as my reference pH for water, and it's 7.29. Now I'm going to add different amounts of 1 molar HCl, and then I'll also add different amounts of sodium hydroxide, which is our base. So just looking at the 1 molar HCl, let's see how the pH readings will be found. So So I'll start with a tiny drop, like just touching the water with the tip of the dropper. And see what it reads. Interestingly, that changed from a 7.29 and now we have a 3.5 something, 3.50. And now I'm going to add 1 drop of HCl. Just 1 drop. And let's see what happens. So the pH is dropping. Remember we started at 7.2, we went down to 3.4, and now we are at 2.59. Now I'm going to add 2 more drops of HCl. Well, this 1 molar HCl is really acidic, as you can see what it's doing. So the pH is dropping again to 2.19. I'm going to do 5 more drops of HCl. And I'm recording all of these values in my notebook. This is 1.83. Then finally I'll do a full drop. Or a full dropper, sorry. So let's see. Just putting all of this. Our final pH reading then is 1.46. Now I'll do the same thing with sodium hydroxide, where I take my pure deionized water, I add 1 drop, then 2 drops, then 5 drops, and finally a full drop, and see the change in the pH reading. So sodium hydroxide is a base. I basically expect that the pH reading will be above 7, because it's basic, it has a high concentration of the hydroxide anions. Okay, so our starting pH for pure water after we added the HCl, after that part, is 4.03. It doesn't make a lot of sense to think that water is a little bit acidic, but just think about it as the starting point, the 4.03. But then when we add the sodium hydroxide, then we expect the pH reading to go up. And so I'll add 1/10 of a drop, which is basically just touching it to the tip of the dropper. Just slightly. Okay, interestingly the pH is going up to 8. This is skipping. Okay. 9.28. 1 drop. Five more drops. Okay, so for the addition of sodium hydroxide, we started at a pH of 4 and ended up at a pH of 12.83 when we added a full drop of sodium hydroxide. So now we are going to add the acid and the base to our buffer system, which we have made from dissolving 1 tablet of the Alka-Seltzer. And after making this solution, I'm going to, this is 100 milliliters of water, so I'm dividing it in 2 to get 50 and then do the pH measurements with addition of hydrochloride, and then I'll do the other 50 with addition of the sodium chloride. So, let's go with that, half and half. This is about 100. Here we go, and I'll take the pH measurement of the solution first before adding any HCl or sodium hydroxide. But I have to rinse my pH meter and my pH probe, wipe it clean with a skin wipes. Dip it in my Alka-Seltzer solution. And obtain the first pH reading. So that's 6.80. Now let's add a tenth of the HCl, tenth of a drop. So remember when we added a tenth of a drop of HCl to pure water, and we had a drop of from 7 to 3. When I just add a tenth of a drop to the buffer solution, we have a drop from 6.8 to 6.75. So it's not as drastic as it was. And so I'll keep doing this, adding 1 drop, 2 drops, 5 drops, and a full drop, and just obtain all the pH measurements. So basically I'll do the same thing with sodium hydroxide. Get the pH readings after adding 1 drop, 2 drops, 5 drops, and a full drop, and you will have these pH readings. So I don't need to do any videos. Yeah. So we're in part 2, which is the fun part of the experiment, where we are going to do the titration experiment. And in here I have 0.109 grams of my unknown number 1 dissolved in 80 milliliters of water. And I added 3 drops of phenolphthalein indicator. So this should tell me that when I have titrated my solution, then the pH indicator will change color, and that's where I stop and find the volume of the sodium hydroxide that I used. Now that I know the volume of the sodium hydroxide used, and I also know the molarity, that means I can get the moles of sodium hydroxide. And that should be equal to the moles of the solution that's being titrated from start to finish. And once I know the moles of that and I know the volume, that should help me find other parameters. So if I know the moles, I can find the molecular mass, and I can also find the Ka. And that's basically what this experiment is aimed at. So for known number 1, we need to determine the Ka and the molar mass, because we are going to take the pH readings, which will also help with the obtaining the Ka values. So let's get started. We have a pH meter here, which I am going to take it out of the water and just insert it in my solution. And as I add various amounts of sodium hydroxide, I'll record the volumes and just as I go, so that I can have the pH of the volume on my Logger Pro. Okay, So I will start with, let's say, let's do 1 ml.
leave the magic.
Alright, so as you can see, when I started the titration, this solution was colorless, and at 14 ml of sodium hydroxide addition, we ended up with a pink color. So I just did more I just did more additions of the sodium chloride just to get a baseline for after the pH changed from 5 to 9, and then it just kept staying in the basic solution. So at the end we have more of the sodium hydroxide in the solution. That's why the pH is really high. And this should give us the pH change and then the Ka values that we need and the volumes that we need to calculate the moles and the molar mass of our unknown solution. So this is it.